All right, let's go over the practice problems. So this says which points on the wave in the diagram are 90 degrees out of phase with each other. Okay, so 90 degrees means that there's a separation of this wave. Now, we have one full wave is over here. So that's our 360. So half of that would be 180. And half of 180 would be 90. So A and B are out of phase, but that's not a choice. So if we look down here, D and E, those are also 90 degrees out of phase, and that's our answer. In number 2, we have a particle, X, in a spring. And it says which diagram represents the motion of the particle X as a longitudinal wave goes by. Longitudinal is like this. It's parallel to the propagation. So our answer is number 2. The vibration looks like that. Number 3 is a superposition problem. So we have wave X and wave Y traveling towards each other. Their amplitudes are going to increase while they collide. That's constructive interference. And they're going to produce a new wave that is 0.6 meters tall. Okay, number 4 is a question that I should have put in the waves part 2 unit, so we'll get into that. This is what's called the Doppler effect. And what happens in the Doppler effect is as a car blowing a horn approaches you, the frequency is high, and then as it passes, it gets lower. And like I said, that was a mistake. That should go in waves part 2. Okay, so in this one we have a musician playing a guitar, and it says that on the diagram, on a standing wave, label one node N and the other antinode A. So we didn't get into this yet. That's in waves part 2, but I'll just go over it. The antinode is the part of the wave that's doing the most vibration. The points that aren't moving are called nodes. So we have our nodes and we have our antinode. It says determine the wavelength of the standing wave on this vibrating string. Well, you can see that this is only a crest. So if we diagram this, here's our wave. Well, what would we have to do to get the rest of the wave? It would look like that. So if this here is 0.62 meters, that's half a wavelength. The full would be double that. So it would be 1.24. And the next part says, calculate the speed of the wave. Well, that's just V equals F lambda. They gave us the frequency. We figured out the wavelength. Just multiply those two numbers. And then lastly, describe what happens to the frequency when the musician shortens the vibrating portion of the string. Well, if they shorten the string, that's going to make the wavelength go down. If the wavelength goes down, then the frequency is going to go up. We haven't changed the medium, so the velocity of the wave has to stay the same. In this one, we have an observer counting 4 complete water waves, and this takes 10 seconds. So we have 4 waves completed in 10 seconds, divide 4 by 10, and that tells us how many cycles in 1 second, and that's what frequency is, 0.4 hertz. And then glass shattered exposed to a sound of a particular frequency. This also is a question that belongs in waves part 2. We'll get into this, so you shouldn't have to know this yet in this part. But for now, when you take a wine glass and expose it to the same natural frequency as the wine glass will start to vibrate and actually break. And this phenomenon, you need to memorize this. There's no other way to know it. It's called resonance.